Growing food on Mars is not simply a question of whether plants can grow. A Mars food system must conserve scarce water, reduce dependence on Earth-built infrastructure, operate before Martian regolith becomes productive soil, support crops that provide real calories, and remain reliable with limited crew time. That is the problem PORES was designed around. Instead of forcing every crop into a single cultivation method, PORES engineers the root environment around the mission, targeting water locally, enabling printable infrastructure, operating before fertile Martian soil exists, supporting crop-specific root zones and staple crops, and building resilience through modularity. The first of those ideas, root-targeted water delivery, actually began before this challenge. We asked a simple question: why water an entire growing volume when only the root zone needs it? So we embedded an algorithmically generated porous tube near the roots, used a local moisture sensor to trigger irrigation only when needed, and stopped the pump as soon as the target moisture was restored. This approach successfully grew red cabbage, showing that localized feedback-controlled irrigation can sustain real crop growth. That early irrigation experiment solved water delivery, but it did not solve Mars. Martian soil must first be detoxified and conditioned, and importing large amounts of growing medium from Earth is not practical. So instead, we engineered the substrate itself. Because explicitly modeling dense 3D porous structures is computationally expensive, we developed a workflow that injects porosity after slicing, separating module design from pore generation. That made it practical to create a hierarchical root zone material with larger pores for root growth and smaller embedded pores for capillary water transport and retention. We then tested whether that added hierarchy actually changed water transport. Under identical conditions, the macro plus micro architecture produced 34% greater measured water loss than the macro-only structure. That increased evaporation is consistent with water reaching more internal surface area through the smaller connected pores, supporting the capillary transport mechanism we designed into pores. Of course, transport only matters if the roots can actually use the structure. Here, we developed dense vertical and lateral roots through pores, while Bengal gram roots followed the engineered channels directly downward. At that point, the printed material was no longer just holding the plant, it was becoming the root zone. The next step was to bring everything together. We integrated pores with precision irrigation, environmental sensing, lighting, and dual camera monitoring in a working grow pod, and then used it to run real plant growth experiments over time. But growing a plant is not the mission, feeding the crew is. So we designed the system from the plate backward. PORES Designer connects each dish to the crops required to make it, and as a crop becomes available, every meal that depends on that ingredient updates automatically. The farm is therefore built around food demand, not simply around what is easiest to grow. And on Mars, food has to do more than meet a calorie target. Our menu delivers roughly 3,000 calories per crew member per soul while maintaining protein across vegan, vegetarian, and omnivore tracks. We also designed for variety and choice, because on a long mission, familiar meals and the ability to eat together are part of crew well-being, not an afterthought. And importantly, that menu is not brought online all at once. It evolves with the settlement as new food production capabilities come online. And producing that menu means not forcing every food into the same technology. Hydroponics handles the crops it grows well. PORES extends production into staples, root crops, and other crops that benefit from an engineered substrate. And protein and processing systems complete the diet. The result is not one farm, it is an integrated food ecosystem built around the crew. The crew does not arrive to a fully mature food ecosystem. Stage 1 establishes the backbone. PORES staples, hydroponic, fresh crops, and an early insect protein pathway come online first, while Earth-supplied ingredients bridge the parts of the menu Mars cannot yet produce. In Stage 2, we build onto the existing backbone. Aquaculture and the aviary expand protein choices, while processing and fermentation turn more of what we grow into usable ingredients. The menu becomes substantially more diverse, even as Earth continues to bridge staples and oils that Mars cannot yet produce. By Stage 3, the system reaches maturity. The remaining staple and oil production comes online. All 7 food production pathways are active, and water, nutrients, and biomass circulate through a much more closed ecosystem. Earth is no longer the foundation of the food supply, it becomes the backup. Once the farm is running, astronauts should not have to babysit it. PORES Ops continuously tracks the environment, water use, crop state, cameras, and hardware health while logging every experiment. Automation handles the repetitive monitoring and control, leaving the crew for the work that actually requires human judgment. On Mars, failure cannot be allowed to become famine. Production is distributed across pressure-isolated halls so a fault is detected, isolated, and the remaining system rebalanced around it. Even after a single hall loss, production continues and no food class disappears entirely. The failure becomes a menu adjustment, not a food security event. Shutdown is not simply turning the system off. Remaining food is harvested and preserved, resources are recovered, and the production loops are cleaned and secured. Reusable PORES modules can serve future crews, end-of-life biocompatible modules can enter a controlled degradation pathway, and future regolith-derived structures remain part of Mars' local material inventory. The goal is simple: leave capability behind, not waste. During normal operation, food moves inward, from production through harvest, processing, and the galley to the crew. The return flow moves the opposite way. Residues enter recovery, where water and nutrients are reclaimed and routed back towards production. Instead of a one-way food chain, the habitat operates as a regenerative loop around the crew. But circularity only matters if the numbers close. At maturity, Earth dependence falls to about 7%. The model water loop reaches 95% closure, with roughly 11 liters of makeup per crew member per soul. Peak connected power is 93 kilowatts and total food system labor remains about 8 crew hours per soul. That is the operating point PORES was designed to reach. PORES began with a simple idea: engineer the environment around the root. Today, we have printed the architectures, measured their transport behavior, grown roots through them, operated an integrated grow pod, and built the software to design and monitor the food system. On Mars, those pieces can grow into something larger, a resilient food ecosystem that progressively depends less on what we bring from Earth and more on what Mars itself can sustain. That is PORES.